Okay, so today is brought to you by a lot of graphs and energy. Okay?
My two least favorite.
Your two favorite
My
things.
two least
Favorite.
Least favorite.
Favorite.
No.
Okay. All right, so this graph looks odd, but you understand this graph. Okay? And you're going, I've never seen this graph before in my life. But let's just don't worry about the graph for now. You have two bowls of water. Okay? You have one bowl of water that's at 20 degrees Celsius. And you have another bowl of water that's at 80 degrees Celsius. Completely filled with the same amount of water. Everything is the same. One's at 20 degrees, one's at 80 degrees. Everything is initially the same except for the temperature. You come back 2 hours later. Which bowl of water is going to have more water evaporated from it? The 80 or the 20?
80.
The 80, why?
Warmer, so more of a change of state.
Think about it in energy.
That's more energy.
Yeah, so now let's just think about this. If you're going to have water evaporate, so here's Wally the water molecule, right? And later on we'll get into the type of bonds that exist, hydrogen bonds and what's called London dispersion forces and all this good stuff, okay? But for water to exist as water, as a liquid, it has to be a little sticky, okay? Not sticky enough to make it solid, right? But it's sticky. Nitrogen and oxygen, which make up our atmosphere, aren't sticky. That's why they're gases, okay? If nitrogen and oxygen were sticky at this temperature, we would have liquid oxygen and liquid nitrogen, okay? Which would get really weird. Yeah, imagine this, like let's say, for example, nitrogen condenses into a liquid at, say, -2 degrees Celsius. Why would that be bad?
Can I have liquid?
It looks like rain, nitrogen.
You would rain liquid nitrogen at -2, okay? What would happen to the vast majority of our atmosphere?
Goodbye.
Bye-bye,
We die.
okay? Very bad things would happen, right? Because literally like, oh, yeah, it's a freeze warning. You have to bring your plants? No, you have to bring in everything because of the fact that the atmosphere is basically going to turn into a vacuum, okay? It's true. Nitrogen, boom, gone, okay? Now, but then when it warmed up, oh, our atmosphere is back. So, yippee. So, if you're going to break the bonds that hold the water molecules together, and this is going to be formed part of a bigger idea, energy always goes in to break bonds, and energy is always released in the formation of bonds. So this is an opening salvo. We're going to spend much more time talking about this concept. I'm just planting the seed right now. If you're going to break bonds that hold anything together, that requires an input of energy. It's a cost, okay? But when you form the bonds, that releases energy, okay? Break bonds, cost you energy. Form bonds, release energy. So this water at 80 degrees has more kinetic energy. So you can think of, and this is what you need to begin to think of in terms of this. You need to begin to think of temperature as being like the radar gun on a molecular level. The higher the temperature is, that means those particles are moving faster. So what's happening is at 80 degrees, there's more particles that have enough energy to break the bonds that hold the water together, okay? At 20 degrees, there's fewer that have that threshold of energy. So the other way that you can think about this, and we talked about this briefly, is that let's say that there's a bar that you have to jump over, okay? And we're going to have two situations. Situation number one, it's a play day with the little second graders, and there's little Timmy, okay? And let's say that it's pretty cold outside, okay? let's say it's like 40 degrees Fahrenheit. And so you're going to take a room full of Timmies and they're going to try and jump over the bar. Well, at 40 degrees Celsius, you're going to have some Timmies that can jump over the bar, but the vast majority of them aren't. Okay? Some will, the more energetic ones, because, and this is going to be important also, when you look at distributions of energies, they all don't have the same. Okay? There's a vast difference in the distribution of energies within a system. We call it 80 degrees or 40 degrees or whatever that is, but that doesn't mean they all have that same amount. Some have more, some have less. We're saying on average, this is how much energy that they have. So, at 40 degrees, some of the Timmies have more energy. They can jump over it, okay? But the vast majority of them run up and go, I can't jump over it. Okay? I'm just telling you.
Poor Timmies.
It's not bad, but just the athletic ones, boom, they
They
can jump over it.
failed.
No, but then it's going to be, the weather's going to warm up, and we're going to go to 80 degrees Fahrenheit. Okay? Now, at 80 degrees Fahrenheit, what's going to happen to the number of kids that can jump over the high bar? It's going to go up, okay? Because now more of them have that threshold of energy that they can jump over the top with. Okay? Makes sense. The same thing is happening here with water molecules. Okay? So instead of a bar that you have to jump over, we're going to talk about energy that it takes to hold that you have to break to hold the water molecules together. So at 20 degrees Celsius, some of them do have enough energy to break away. But at 80 degrees Celsius, you have a lot more of them that can jump over the bar. Okay? Does that make sense? All right. Now, let's go back and look at this graph. So this graph is a little bit counterintuitive. So the lower graph is actually the higher temperature. The spiky graph, which is not necessarily descriptive, but you get the idea, is 70 degrees. Okay, so everybody looks at this graph and everybody wants to think the taller one to be the higher temperature. Okay, but it's not. But you have to understand what the graph is. So the graph is showing the number of collisions, and this is how much energy the collisions have. Okay? And this vertical line is the activation energy. So if the reaction is going to happen, the collisions have to be above that activation energy. Okay? So what this tells me is that on both of these, the vast majority of these collisions are below the activation energy. The vast majority of the kids aren't jumping over the bar. Okay? The x-axis is telling you how many collisions are occurring at that particular energy. So if you look at that upper line, which is the 70-degree line, what's that saying is that the vast majority of those collisions are happening with this amount of energy, 5 to 10. Don't worry about the scale for now. I just put numbers up there so you get an idea of what the numeric values are. So the vast majority at 70 degrees are in this 5 to 10 range. You have a very small number of those collisions that are above the 20. So 20 is the cut line. Okay? If the collision occurs above the 20 line, free at last, free at last. Good God Almighty, you are free at last. The energy is high enough that we can start the reaction, or you can break the bonds that hold it together. Okay? So, on the 70-degree line, a very small number of those collisions is taking place above the activation energy. This is why yesterday, when you all had that at the cold temperature, why did it take so long in terms of this graph? Yeah, so the vast majority of the collisions were below that activation energy. Some of them were. We didn't make it so cold that we shifted this line, if we shifted this line and made it so cold that it was right here, the reaction would never happen because it would be too cold. Okay? So on the cold line, you had a small number of collisions that were above that activation energy. Okay? Just not very many of them. Now, at the warmer temperature, at the 90-degree line, that one, you have, what you've done is you flattened this out. So what we've done is we've shifted more of these collisions where they have more energy. Okay? Same total number of collisions, we've just shifted it to the right. So on the 90-degree line, now we have a much larger number of collisions that are above that threshold. So this is why the reaction that you ran when it was warm, bam, might have taken 30 seconds to happen. Because so many of those collisions were above that activation energy. Okay? Does that make sense in terms of what you all saw yesterday? Cool, got it, great. All right, should make sense. Okay. Graph number 2. Oh, chill out. Let me do a little writing here.
I'll just get an old one.
Okay. Actually. Oh. Kevin, stop that camera. I'm sorry.